once again a nice interesting example I would say, where we link measurements and equation of continuity. Okay. Though not a core chemical engine example from ocean engineering I would say, but anyway fluids are common to everybody. So, we will still discuss this. Okay. First what is the measurement we take? So, you have to imagine, you can go to a seashore and imagine yourself standing on a seashore or ocean shore, and on the surface you are measuring the x and y velocity components. So, these velocity components are measured. It is supposed that it is easier to measure these velocity components compared to the downward velocity. So, what we do, we measure the x and y velocity and use the continuity equation to estimate the downward velocity. That is why the title says estimation of vertical velocities in ocean. Okay. And those velocities are shown here. So, let us read the problem. The figure shown gives the x velocity and y velocity measured at the surface of the ocean in meters per second. Taking the z velocity as 0 at the ocean surface, what is z velocity at a depth of 50 meters. Okay. Now, let us look at this figure shown here. First, the distance are what is shown here are measurement points. There is one measurement point here, and then one measurement point here, another measurement point here, another measurement point here, something like taken a region of ocean and dividing into 4 zones. But of course, we are in the ocean. So, look at the distances, they are order of kilometers, 500 kilometers, not even order of kilometers, order of hundreds of kilometers. So, the x distance between the measuring point is 500 kilometers, the y distance is 540 kilometers. Okay. What is shown here? Let us take this point, the x velocity, let us take this point, the x velocity is the negative direction. So, minus 0.25. What is the y velocity? Y component is 0. So, just there is no dot or arrow there. These arrows are shown proportional to the velocity values. Okay. Let us take this region. In this region, once again velocity is in the negative direction, same value minus 0.25. You see a small component of velocity in the y direction, it is minus 0.01. Okay. Similarly, let us take this zone. Now, the x velocity is in the positive direction 0.3, because ocean you can have any x velocity, y velocity can vary from region to region. Y velocity is also positive, a small value 0.03. Similarly, in this zone 0.25 and 0.05. That is how we understand the measurements shown here. Now, before we proceed solving, we need to discuss about the choice of coordinate axis. Different books uses different coordinate axis, and that is relevant to this particular example. Let me, you will understand why I discuss now here. Okay. Now, this choice of coordinate axis, remember all of them are right hand coordinate system. Okay. Now, the first coordinate system what is shown here is a axis which I have chosen so far, and that is what we will also continue to choose almost throughout the entire course. Now, in this coordinate system, the horizontal axis is x, vertical is y, and of course, the axis towards us is a z axis. Okay. Now, what is the advantage of this axis? Okay, let me come to that little later. Now, what I have shown in the second figure is that I have changed the axis. What I have done here is I moved x here, I moved y here, and then moved z here. Okay. So, now the horizontal axis becomes z, the vertical is x, and the axis towards us is y. Now, I do one more rotation this way. So, I move x here and then y here and z here, you result in this axis. So, what happens now? The horizontal axis is y, the vertical is z, the axis towards us is x. Now, our attention is the first figure and the third figure, not the usual coordinate axis which are used in books are the first and the third. So, we will discuss them, not the second one. If you look at the first choice coordinate axis, what is the advantage? If you look at the front view, you can easily reduce to two dimensional case, you just have x axis, y axis. What is the slight disadvantage? Gravity acts along y axis, of course negative y axis, which is not so conventional. Moment you say some position, you always say z, let us say some datum is there, z equal to 0.5, z equal to 0.5. So, traditionally and always the direction along which gravity acts is z. So, that way it is slightly unconventional. Okay. So, let us come to the third diagram. Here gravity acts along z direction. So, along the conventional z direction, but what is the disadvantage? Suppose if you want to reduce to 2D, you will have to look down, of course the top view, of course maybe it will turn, then you will have x axis here, y axis here, okay. That way slightly inconvenient, but this is the axis which is used in this problem. What did I say? I say on the surface of the ocean I have x here, y here, and then z axis is here, of course into the ocean it will be negative. So, the third choice is what is applicable for this particular problem with z axis along the vertical direction, okay. So, these are the different choice of coordinate system. You will usually come across the first or the third, and second is rarely used, okay. So, let us proceed with this coordinate axis, keeping this coordinate axis, the third one keeping in mind, that is what is of course used here, okay. Now, what is that we are going to do? We are going to use the continuity equation. Once again we will assume on an average it is steady state and assume incompressible flow in the ocean, okay. And we are, remember it is a 3-dimensional case because we have all the 3 components. We are going to apply this continuity equation at the point E, the point E. What does that mean? I need values for this derivative dou v x by dou x, I need derivative dou v by dou y at E, then I will find out what is dou v z by dou z, hence v z, that is the whole idea. I want to evaluate the first 2 derivatives at E. How do I evaluate? Okay. To evaluate the dou v x by dou x, I will evaluate at A. How do I evaluate? Because I know v x here, I know v x here. To evaluate the derivative, I need the velocity x velocity at 2 points which are separated along the x axis. That is what you have a measurement here, you have measurement here. Using that I can find out what is the derivative at A. Similarly, I will use these 2 v x values, find out what is the derivative at B, take an average and I will get the value at E. So, let us do that. Similarly, we will do for the other direction. So, at point A, dou v x by dou x, I use approximation sign because the partial derivative is expressed in terms of the difference, okay, difference expression, delta v x by delta x. What is delta v x? I have minus 0.25 here, this minus of minus 0.25, both values are same. So, resulting in just 0, okay. So, dou v x by dou x is equal to 0 at point A. Now, let us consider point B, dou v x by dou x is equal to once again delta v x by delta x. Now, what are the velocities? The velocity here is 0.25 minus of 0.3, okay, divide by the distance between them in terms of meters. That is why you get a value like minus 10 into, it is a negative because 0.25 minus 0.3, you get a value of 10 power minus 8 because of the large distance, the unit is 1 by second. Okay. Now, to find out dou v x by dou x at E, I take the average of values found out at A and B. We do all this because it can be highly fluctuating, we need to arrive at some average value, that is why we make measurements, divide into 4 regions, make measurements, make 4 measurements, find from that to find 2 derivatives, find average, all these are done to average out. Okay. So, find out mean values at A and B, which means that average of these 2 values, which gives me minus 5 into 10 power minus 8 1 by second. Let us exactly do the same thing for the y direction. What do? I take point C, I know 2 velocities. To find out dou v y by dou y, I need v y at 2 points separated by y distance along the y direction. So, I take these 2 velocities, find out dou v y by dou y at C. Similarly, take these 2 velocities, y velocities, find out dou v y by dou y at D, then take average. Okay, let us do that. Of course, the x velocity decreases, it is a negative, so decreases in the x direction. Yes. Okay, let us proceed to the y and the derivative dou v y by dou y at point C. So, once again dou v y by dou y is delta v y by delta y. What are the velocities? It is 0 here and then minus of 0.03 and the distance between them is 5.4 10 power 5 meters, 540 kilometers, okay. And so, you get a negative value, okay, minus 5.56 10 power minus 8. Now, at point D, let us evaluate dou v y by dou y. What are the values? I have minus 0.01 here and then minus plus 0.05 divide by 5.4 10 power 5. So, you get a value of minus 11.1 10 power minus 8. Let us take average of this two values, this and this, okay, which will give us dou V y by dou y at E. Okay. So, at the same point we have got the first value for dou V x by dou x, which is change of V x by with respect to x. We also obtained dou V y by dou y, change of V y in y direction, that is also negative. So, y velocity also decreases along y direction. That was our objective, at the same point evaluate these derivatives. Now, let us substitute in the continuity equation to find out the dou V z by dou z equal to 0. So, let us substitute, we will write for dou V z by dou z, that is our unknown, okay, as minus dou V x by dou x plus dou V y by dou y. Substitute the values, okay, that gives us a positive value, because these are negative values, we have negative sign here. So, the z velocity increases along the z axis, along the positive z axis, which means down the ocean it decreases. Okay. Okay, z velocity increases in the positive z direction, the ocean of course in the negative z direction. If we go down the ocean, the z velocity decreases. So, if you start with from the ocean, it decreases. Okay. So, now we are asked to find out what is the velocity at a particular depth, okay, which means that we will have to integrate this. We will assume all these are does not vary with spatial location, okay, that is why it is a constant, okay, and then integrate. We integrate from the surface of the ocean down the ocean. Okay. So, the limits of velocity are, we are said that the z component of velocity is 0 at the surface, and we are asked to find out what is the z velocity at distance of 50 meters. What is the limits for z? Z is 0 at the surface of the ocean, because we are going down the ocean, it is minus 50 at depth of 50 meters. Do this integration, okay, and you get the velocity as 6.67 10 power minus 6, it is a negative. So, to get a quick idea, to get an idea of what this velocity is, 0.58 meters, or you will be travelling 0.58 meters per day. So, in a day you will travel only roughly 0.6 meters, very low velocity. Of course, it is down. Remember, our x and y velocities are extremely large, they are order of some meters per second, etc., but now our z velocity is extremely low. Maybe that is the reason it is difficult to measure the z velocity, but measure the x and y velocity. So, very good example I would say, linking measurements along two velocity measurements along x and y axis, finding that, using that to estimate the z velocity component using the continuity equation. Okay, the last example as usual including the transient term. Let us discuss the geometry first. I have a cylinder with a piston, a well known geometry, let us say you would have come across in thermodynamics and mechanical engineering class, etc. This could be a cylinder and engine or reciprocating pump, etc. Okay. Of course, we are considering a gas here, and you have a piston which moves at a constant velocity V p. Okay. So, let us read the problem. A piston compresses gas in a cylinder by moving at a constant speed as shown in figure. Now, let the gas density at and length at time t, some time t equal to 0 be rho naught and L naught. What does it mean? In this region the density is a function of time, at some time t equal to 0 it is rho naught, and this length keeps changing with time, at some time t equal to 0 it is L naught. Okay. Let the gas velocity vary linearly from V x equal to V p at the piston face to V x equal to 0 at x equal to L. What is the meaning of that? Remember, we have been telling always that at a surface the fluid clings to the surface, okay, which means that it gets the same velocity as that of the surface. So, now this velocity, this surface moves at a velocity of V p. So, the velocity of the fluid in that which is attached or which is clinging to that surface also V p. Now, this surface of the cylinder is stationary. So, velocity of fluid in this region or at that surface is also 0. That is why it says let the gas velocity vary Of course, we are making assumption that the variation is linear. What I explained is the condition that V x equal to V p at the piston face and V x equal to 0 at x equal to L. They are nothing but the velocity of the piston at the face of the piston and velocity of the surface of the cylinder, which is 0 at the other side. Okay. That is why the conditions are V x equal to V p and V x equal to 0, and it varies, we are assuming it to vary linearly. Remember, at x equal to L is because L is a function of time, we cannot say a fixed time, that is why it is L. If the gas density varies only with time, what does that mean? In this region, in the cylinder, we are assuming density to be constant throughout the volume. So, that is why gas density varies only with time. Find an expression for rho of t. How does the density vary as a function of time? We are not accounting for spatial variation. Now, let us start with the differential total mass balance. Now, remember density varies, okay, varies spatially. So, I cannot use a simplified form, okay, and we just have only one dimensional case. Okay. So, I simplify it and write as dou rho by dou t plus dou rho V x by dou x. Remember that I have not ignored this term, I have not taken rho out of the spatial derivative. Now, if you assume density is uniform inside the cylinder, after this assumption I am not saying density is not a function of time, density assumed to be uniform inside the cylinder. Now, I take out of this derivative. So, density plays a role in this form of the equation. All our earlier equations we never saw the density at all, okay. Dou rho by dou t was 0, rho was taken out, that also vanished. So, in this particular case, after we assume the density is uniform inside the cylinder, then I take out the derivative, okay, and both of them become total derivatives because density is a function of time only. So, d rho by dt, V x is a function of x, and so dV x by dx. Now, we need to find expression for the velocity. We are told that the x velocity varies linearly, and let us find out what is the expression. A simple expression, what is the condition we are given? X equal to 0, this x equal to 0, the velocity is velocity of the piston, x equal to L, the velocity is 0 and the variation is linear. So, if you take V x equal to A x plus b, we have two conditions to find out the two constants, that is what we are going to do. Okay. Let us assume V x is A x plus b, find out the constants. First, x equal to 0, so we will substitute x equal to 0 here, left hand side the velocity is V p, and of course right hand side we have b here, which means that b is equal to V p. Now, what is the other condition? X equal to L, please remember L varies with time, L varies with time. Okay. X equal to L, the left hand side velocity is 0, and then substitute x equal to L here, we have A L here and then plus b, b is nothing but V p, we have already evaluated, and then this gives you A is equal to minus V p by L, the constant. So, let us substitute in this equation and then find out that the velocity variation with respect to distance follows this relationship, okay. V x equal to V p into 1 minus x by L. Okay. When x equal to 0, we have V p, x equal to L, we have 0. Of course, it should obey those conditions. What is that we have found out? We have found out V x as a function of x. Why do we do that? Because we want to evaluate the derivative. Okay. Of course, what is L? L is equal to the initial length L naught, and then over a period time t, this piston would have moved V p into t. So, the effective length or remaining length is L naught minus V p into t. To time t equal to 0, it is L naught, over time period t, the piston moves a distance V p into t. So, the remaining length is L naught minus V p into t. That is what I have been always been emphasizing, that L is a function of time, L is a function of, it decreases with time. Okay. Now, okay, the one dimensional differential total mass balance which we have written is d rho by dt plus rho dV x by dx. So, let us substitute here. Okay. We have got an expression for V x, let us differentiate that and get minus V p by L, okay. And substitute it here d rho by dt, and for dVx by dx it is minus V p by L, resulting in this equation. We are proceeding towards evaluating rho as a function of time, okay. So, let us do that. D rho by dt, repeating the same equation here, L is equal to L naught minus V p t, it is a function of time. So, let us use separation of variables. We bring rho here, d rho by rho here is equal to V p by L into dt. We will substitute for L, it is a function of time. When I integrate here right hand side, L is not a constant. So, before integrating we should substitute in terms of time. Now, let us integrate. At time t equal to 0, density is rho naught, at any time t the density is rho, those are the limits for the left hand side. Right hand side of course, the limits are 0 and then time any time t. Now, let us do the simple integration. We have ln rho by rho naught on the left hand side, and then right hand side minus ln L naught minus V p t, between the limits substitute the limits t and 0, and then you get this expression ln L naught by L naught minus V p t, from which we get expression for how density varies as a function of time. So, rho depends on time for given initial densities, initial length and velocity of the piston, those are the variables. So, if you give me the velocity of the piston and initial density, initial length, this expression gives us how does density vary as a function of time. Okay. Okay, so, with that we have concluded all the applications. So, let us summarize this part on the differential total mass balance equation. We started with the integral total mass balance equation for a small control volume and obtained the differential total mass balance equation by stringing it to a point, also called as a continuity equation. And it had two terms, one was time rate of change of mass, other term was net flow out of mass by convection, but emphasis on per unit volume, that is what was density. Okay. And we simplified for of course compressible, incompressible. Within the scope of this course and most of the courses in your engineering curriculum, you will be restricted to incompressible flow. So, that form is more important, which we will come across repeatedly later. We looked at applications of differential total mass balance equation. What are the applications? We checked given velocity components, we found out one velocity component given the other. We also used integral and differential balance to find velocity field, and we estimated one velocity component based on experimental measurements on two other components, and finally an example on the rate of change of density with respect to time.